Good morning. Today we are going to kick off Unit 6 by doing 6.1, which is going to be polar coordinates. So, interesting. Thanks for the note in there, Dakota, about Unit 6 opening. Next time, just let me know through Kmail and I can fix that for you. So Unit 6 is our last unit of this semester, which is very exciting. And there is no final exam for this class, just like last semester. The course is hard enough, and by the time you get to the end, I don't feel you guys need a final exam. So this will be your last test at the end of this unit. So yay, that's kind of exciting. So polar coordinates are going to teach us how to graph on a different kind of plane. So we're used to graphing on a coordinate plane that has an x and a y axis, but polar coordinates, we're going to be able to graph on a circular shaped graph. So that's how, well, you'll see in just a moment. So here's the one that we are familiar with, right? We're familiar, like if I say graph 2, 3, we know we go over 2 and then we go up 3, and we have that point, 2, 3. Our polar coordinates are going to be on a circular plane, which is kind of interesting. It starts at 0 over here on the x-axis, and we're used to this because of our unit circle, correct? We're used to sort of the way that this looks. So we're used to having our angles in radians, pi over 12, pi over 6, pi over 4. But what we're going to notice is that unlike a unit circle, this also has little tick marks going out from it. So this is the way we're going to be able to count today. So if I say, let's do an example here. Angles are measured from the positive x-axis. So again, we're going to start here at 0, and then we go up and around to the left. So points are represented by a radius and an angle. Hint, 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 this just might be your essential question for the day. So unlike a traditional and rectangular coordinates, here is our polar coordinates. It's radius comma theta, or radius comma angle. This very, very center is called the pole. The center of the graph is called the pole, hence the name polar coordinates. So we're going to try one here. If I ask you to graph 4 pi thirds, let me show you how that works. Starting from the 0 on the positive x-axis, we're going to go up to pi thirds, which would be right there. And since it says 4, I'm going to start at the pole and I'm going to go out 4 points. 1, 2, 3, 4. There we go. So that coordinate right there is 4 pi thirds. Does that make sense how I found that on the graph? Can I get a smiley face or a check mark? So we're going to do the radian first, the degree first, and then the radius second. And again, the radius is just going to be how far out we go from the pole. So far so good, not too difficult. What if I ask you to graph 5 pi over 4? That means we would go to pi over 4 first, and then for 5, we would go out 5. 1, 2, 3, 4, 5. And that would be my coordinate. So everybody's good when they are both positive, correct? Because we're going to try some harder ones now. And they're not really harder, they're just different. Okay, so let's try the next one. So this time, notice, my angle is a negative. So how are we going to do negative angles? It just means instead of going to positive 3 pi over 4, which means I would start here at 0 and I would go to 3 pi over 4, instead of going in the positive direction, you would do the same amount but in the negative direction. Everybody okay with that idea? And then it's still at 3, so we're just going to go 1, 2, 3. So positive angles go in the positive direction, negative angles go in the negative direction. Now, what do you think is going to happen if I make this number a negative? Can you guys take a guess for me? So what if it was negative 3 pi over 4, meaning I do go this way, but what do you think I would do if instead of doing a positive 3, it was a negative 3? Any ideas? Just getting you to think about it before I show you. Dakota, you're absolutely right. So let's try. Down here, I have positive 2 pi over 3, but the front number is a negative 4. So that means we always do our angle first. So let's go positive 2 pi over 3. But instead of going out 4, 1, 2, 3, 4, it's a negative 4, which just means you're going to go in the opposite direction. 1, 2, 3, 4. Negative 4. Everybody okay with how I got that? So let's quickly review. Positive angles go in the positive direction. Negative angles go in the negative direction. If your radius is positive, you just go straight up on the line that you were at. If your radius is negative, you go in the opposite direction of where you were at, of where you ended at for your angle. So here's what I want you guys to think about for a minute. Let's check this one out. If I'm going to plot 7 comma pi over 2, I can go to pi over 2 and I can go out 7. And I get this pink dot right here. Think about regular coordinate planes for a minute. There was only one way to get to 2 comma 3. And that's if it says 2 comma 3. There's only one way to get that dot. What's unique about our polar coordinates is there's many ways to end up at this one spot right here. Can you guys think of another way? How else could I end up at this spot right here? Can anybody think of another way I could write this? Let's think for just a minute. Let's see if we can come up with one. Excellent job. Yes. So another way that I could end up there, there's actually lots of answers. I'm going to show you four different answers. But the one that Dakota typed in was negative pi over 2. So let's try that. Negative pi over 2 is down here. You are absolutely right. And then how could I end up at this dot up here? And Stefan, you're right. You're also correct. Negative 7. So negative pi over 2 means I'm going to go down. And then negative 7 means I'm going to count up backwards the other way to negative 7. That was cool. So far we have 2 ways that I could get there. I'm going to show you 2 more ways. Just broadening our horizons a little bit. This one right here will get us there. So negative 3 pi over 2 means I'm going to go in the opposite direction. So here would be pi over 2. Here would be an additional pi. So negative 3 pi over 2 and then a positive 7. Everybody okay with why that one works? So this is what we were talking about a moment ago. Unlike a rectangular coordinate system, there's many ways to list the same point. So it's kind of cool. I'm going to show you another way. This is actually the one you guys just gave me, the negative pi halves and then a negative 7. That also gets us there. There's one more that I want to show you. And that is, when we're talking rectangular coordinates, I'm allowed to go around more than one time. Right? I can keep going around and around and around and around as many times as I want to. So actually there are infinitely many ways to represent this coordinate. So another way would be this one, 5 pi over 2. Notice if you divide that out, you would get a whole pi and then half of a pi. So a whole rotation plus a pi over 2 rotation. So that's sort of this little, anyway, it's one of these crazy arrows that wraps all the way around and back up to pi over 2 and then goes up 7. So there's many, many ways to write the same point. Now we're going to take a point starting in the rectangular coordinate system and we're going to convert it to polar. So can you guys write this one on your paper? I want you to have one completely worked out example of how to start at rectangular and transfer it into polar. So the first thing I want you guys to do is draw in your right triangle. When I draw in my right triangle here, we know that if it's 3, 4, that means on the x-axis it's a distance of 3. On the y-axis it's a distance of 4. Theta is the angle in between that this makes, and r is your radius. So is everybody okay with my labels, how I got those labels? Okay, great. So now what we need to do is we need to solve for r, right? So it's Pythagorean theorem. 3 squared plus 4 squared equals r squared, which we know that's going to give me that r equals 5. Right, 9 plus 16 equals r squared, so r is the square root of 25, which is 5. So we found my r is 5. How am I going to find theta? Well, it's telling you we can use the trig that we know in order to solve for our theta. So here's one way to do that. I can say tangent. So tangent opposite over adjacent, right? So tangent of theta equals 4 over 3. So when we type that in our calculator, remember, you're going to type it in as second tangent, or it should say tangent to the -1, 4 over 3. Can you guys see if you got 0.93? Try it in your calculator. Second tangent 4 over 3. That would have been my work phone on my desk. That was nice. Can I get a smiley face if you guys got 0.93? And if you didn't, change your mode, right, to radian. So sometimes it's going to want your answer in degrees, sometimes it's going to want radians. So just pay attention to how the answer is listed on the quiz or the test. So how do I write this in polar coordinates? Well, remember, polar coordinates are r, comma, theta. So I would write it as 5, comma, 0.93, r, comma, theta. Everybody okay with our steps here? So they gave us our rectangular coordinate. I put it on a graph so I could see what it looked like. But basically what we do is Pythagorean theorem to find your r. Then you're going to use one of your trig functions. Okay, let's generalize this. So that way we have a formula that will always convert from rectangular to polar. So here's your general rule. We're not going to plug in numbers, we're just going to leave it with letters. So by the time I solve for r, we get that r, my radius, is always going to be the square root of x squared plus y squared. So can you have that on your paper, please? So what I would have in my notes, I would write the words converting from rectangular to polar, and here's how you're going to find your r. We proved that this was true on the last slide because it's really what we're doing by the time we draw that rectangle, but this is just a rule to help formalize it for you. Okay, and then from there, you're just going to do tangent theta equals y over x, opposite over adjacent, and to solve for your theta, that means we're going to use second tangent y over x. So these two highlighted ones are going to be your shortcuts for converting from rectangular to polar. When you have the highlighted portions on your paper, can you two let me know, please? And the first two or three times that you guys do this in your checkup, it would probably be a good idea to draw it just so that way you're getting a visual of what's going on, even though we have these really cool shortcut formulas for ourselves. I just like you guys to be able to sort of see what's happening. All right, now let's go the other way. So now we're going to go from polar to rectangular. So write that in your notes. Polar to rectangular. Because if we can go one direction, we should be able to go the other direction. So my polar coordinate that I'm giving you is 4, comma, pi over 4. And what does that look like on our polar coordinate plane, basically? Well, it's up at the pi over 4 mark, and it's out 1, 2, 3, 4. That means your radius is 4, and your angle was pi over 4. Is everyone okay with how we drew this triangle? Radius is 4, angle is pi over 4. So this time we have to ask ourselves, what trig can I use to go the opposite direction? I need to solve for x and I need to solve for y. Okay, so let's just pick one. We're going to do cosine first. So if I do cosine of pi over 4, cosine is adjacent over hypotenuse, so my adjacent is x over my hypotenuse, which is 4. So let's write out that equation. All we need to do is solve for x. We're really close, right? So how am I going to get x by itself? What do you guys think? What do I need to do? I'm going to multiply by the 4. That way the 4's go away. So I get x equals 4 times cosine pi over 4. Using your unit circle, what's cosine of pi over 4? Do you have your unit circle handy? Cosine of pi over 4 is root 2 over 2. So my x equaled 4 times cosine pi over 4. So here's my 4, and I'm replacing cosine pi over 4 with root 2 over 2, because that's its value. 4 times root 2 over 2. The 4 and the 2 cancel to 2, so we're getting x equals 2 root 2. Are there any questions how I did that? Probably you just need your unit circle handy. We okay so far? Okay, great. Now let's find my y. So what trig function can I use for y? If I need to do opposite over hypotenuse, that's going to be sine, right? Now let's set up a sine function. Sine of pi over 4 equals my opposite over my hypotenuse. Let's write down that equation. Again, my goal is to get y by itself. So to get rid of the divide by 4, I'm going to multiply both sides by 4. So y equals 4 times sine pi over 4. So if I'm looking at my trig function, my unit circle, sorry, sine of pi over 4 is also root 2 over 2. So 4 times root 2 over 2 equals 2 root 2. So my x and my y happen to be the same in this case. So I got root 2 over 2, comma root 2 over 2. Those are my rectangular coordinates, my x, comma y. Any questions before we do a generalization of these formulas? Okay, sure. Yep, so let's go over the generalizations for the formulas. Did you guys notice that when we are back up here and we were trying to find our x value, we are going to use cosine. When we're trying to find our y value, we're going to use sine. So here's going to be our general formulas. So my cosine of theta is going to be my adjacent over hypotenuse, so that's x over r. So make sure you write that down, which is what we did in the last slide. This is just without any numbers in it, right? Just using variables. And again, if we're trying to solve for x, then really the formula that we're using is x equals r cosine theta, because we multiply both sides by r. Okay, so that's your generalization for finding x. Now let's try y. So y is going to be the same thing except with sine. So when I come over here, my sine theta equals opposite, which is y, over hypotenuse, which is my r. So you guys go ahead and write your yellow equation for y equals, and then I'll show it to you, but you should have it pretty easily. Exactly. So y equals r sine theta. So now if I ask you to convert from polar to rectangular, you can just use these two formulas. Isn't that handy? Super handy dandy. Because all you need is r and theta. r and theta, and r and theta is what I give you. Those are your polar coordinates to plug in. So very, very simple. Okay, one other way that we are able to represent points on a polar coordinate is in degree, because we know that these degrees are the same in radians, right? So this would be pi over 4, this is pi over 2. So they're just showing you you can do this if you're talking in radians or if you're talking in degrees. So let's start with the blue one up here. 8, 210 degrees. So we start at 0, we go around to 210 degrees, and then we count out 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. We get our blue. Negatives work the same way. So if it's 6, negative 120, instead of going in the positive angle direction, you would go in the negative angle direction and then go 6 spots out. If it's your radius that's negative, you're still going to do your positive degree to 300. 300, but because it's negative, I start at the pole and I go in the negative direction. 1, 2, 3, 4, 5. So these work the same way as they did before if they were radian. I'm just showing you that sometimes you're going to have it in degree. You guys okay with that? Wonderful. Don't you like 6.1? I do. It's kind of fun. It's like a really good, nice little mathematical break for our brain. Okay, couple last things. Convert the rectangular coordinate system to a polar coordinate system. So here's your rectangular coordinate system. And before we convert it to polar, I just wanted to show you what it looks like on a graph. We know that x squared plus y squared equals r squared is a circle. Since my r squared is 9, that means my radius is 3. 1, 2, 3. So I'm just showing you a picture of what that looks like. So what are we going to do next here? So we said our r's are plus or minus 3 because we know that radius, it could go in the positive direction or in the negative direction. It's going to go both directions. So here's what it would look like on a polar system. On a polar system, they're saying that they only made each unit a half of a unit, so this is counting out 3. 1 whole unit, 2 whole units, 3 whole units. I don't know why they did that. They probably should have just gone 1, 2, 3 and just gone by 1, but sometimes they like to switch it up. So if each unit's only a half and we're going out 3, just make sure you count 3 whole spaces out. So on the polar system, it's going to be the same. It's still going to be a circle, and it's going to be the 3 in all directions. But since there's no restriction on your angle theta, what they're telling you is that the circle is continuous, meaning it can keep going around and around and around and around. So how many answers do we really have? Infinitely many, because there's no restriction on your angle. Everybody okay with that? Because I could say 5 pi, and you would have to go around, 2.5 times. I could say 10 pi. So that's the only difference when we're changing from a stationary circle on a coordinate plane to the polar. Polar has infinitely many solutions. Okay, so here's one way that they're going to write it. Instead of having a 9, let's say that it was an r squared. How can you solve for r? It's just what we wrote down already on one of our previous slides. So r is just the square root of x squared plus y squared. That would be for the generic. But that's already on your paper from earlier. So let's try this one. Convert the rectangular coordinate system equation to a polar coordinate system. So what are the polar conversions we found for x and y? Oh, so here's your question. Sorry. Let me show you your question. Your question is right here. I'm sorry, I didn't want you to see all that in the beginning because it's a little confusing. There we go. So if I give you this equation right here, everybody write that on your paper. This is an equation in your rectangular coordinate system, and I want you to change it to a polar equation. We know it's rectangular because it has x's and y's. Our polar system is going to have r's and thetas. You guys good with that? Right? Rectangular has x's and y's. Polar has r's and thetas. So if it's asking me to convert it, all I need to do is I need to plug in the formulas that we found earlier today, which are these. So we found that x equals r cosine theta, so I'm going to put that where I see my x. We found that y equals r sine theta, so I'm going to put that where I see my y. So let me give you guys a minute to try that on your own paper. Plug them in, substitute them in for x and y. So yours should look like mine. We basically just took our r squared theta, r cosine theta, and put it right where we saw the x. So since the x was x squared, I have to do that whole term squared. This one is going to go where I see the y. So out in front there was a 4. It's going to get replaced where I see the y, r sine theta. So let's see how they simplify this crazy thing. They just squared both terms. That was easy. R squared cosine squared theta. And they distributed the 4. Just multiplied it by the 4. Okay, so and that's it. So that's your answer. You can circle your final answer. There's a little note down here. It says we wouldn't recognize what this equation looks like in polar coordinates, right? We don't even recognize this equation at all. We're not used to that equation. But looking at the rectangular version up here, we know that it's a parabola. So how do we know that this one's a parabola? Just a quick reminder. If you got y by itself, if you divided by 4, you would get y equals x squared divided by 4. X squared equations are parabolas because they're quadratics. Quadratics are always parabolas. So they're just kind of making a little note that we are not used to the polar form yet, but from the rectangular form, we can somewhat identify what the graph would look like. So they're just making a little point there that we're way more used to this than we are used to this. But did you guys understand the steps okay? So when we change from rectangular to polar, you're just going to take your x, plug it in, take your y, plug it in, and then it's in your new format. All right, so that wraps it up for the day. 6.1 is not too difficult.